Let's go through the boundary layer theory. We'll be revising boundary layer theory through concepts, through questions. The first question said that the boundary layer thickness is the distance from the boundary to the point where velocity of the fluid is equals to that of free stream velocity. So we know that in boundary layer theory, as the boundary layer progresses, we observe, be it in the laminar region, transitions region, or the third turbulent region, when the velocity profile reaches the boundary layer theory, the velocity reaches theoretically up to 99% of the free stream velocity, often represented through u infinity or v max. So hence 99% is the correct answer. The second question asks, for laminar boundary layer, its thickness is expressed by the relationship. For laminar, we know that the relationship goes like this: 5x by root under rx. Now, often in some notes, we observe that delta is often written as 4.64x upon root rex. So that is what? It is being derived using Blasius equation, and there are different iterations of the Blasius equation. This one particularly is derived when we use a cubic profile, where it is written as the ratio of local u by free stream velocity is 3 by 2 times eta minus 1 by 2 times eta square, where eta is nothing but y by delta. When you do it, you will get 4.64, but when you use the exact Blasius equation, the delta will come out 5x by under root rex, which is generally asked in the examination. Here you can see that for the laminar boundary layer, the boundary layer thickness is 5x by under root rex, and the variation is like this: delta is directly proportional to the root under value of the x, where x is the distance from the leading edge of the plate. And similarly, we have for the turbulent layer, we have 0.377x upon rex to the power 1 by 5, which is x directly proportional to 4 by 5. Now, if you compare at one, and in the laminar boundary layer, the boundary layer thickness is directly proportional to the value of x to the power 1 by 2, that is 0.5, whereas in the turbulent boundary layer, we have it is proportional to 4 by 5, which is 0.8. So one can clearly see that in terms of values, this gives you a higher result. So this question also comes that in which case do we get a higher thickness of the boundary layer. So it is turbulent boundary layer where the thickness is higher. It is because of its higher power. Then comes the local skin friction coefficient. It is 0.664 by root under rex for the laminar, and 0.059 divided by re to the power 1 by 5. This is also asked in the exam. And then there is average skin friction or drag coefficient. It is twice of this value for laminar, and it is 5 by 4 times of this value for the turbulent. One has to keep this in mind. Now we can also see this one thing, that the skin friction coefficient or the local skin coefficient is given by nothing but CFX is often depicted as the wall shear stress divided by 1 by 2 density upon free stream velocities square. This is a dimensionless entity, and it measures the shear stress at a point related to the dynamic pressure, where half rho v square is nothing but the dynamic pressure. So one can summarize that for laminar boundary layer, one can keep these values in mind. That first is your delta, that is your boundary layer thickness, is equals to 5x upon root under rex, where r is the Reynolds number, where x is distance from the leading edge. Second term is the shear stress, the wall shear stress in terms of Reynolds number. It is given by 0.365 mu, the dynamic viscosity mu infinity root under Rex whole divided by x. The third entity is your local skin friction. CFX is given by 0.664 upon root under Rex. And the fourth one is the the coefficient of drag, or the average coefficient. It is given by C D as 1.328, it is twice of it, divided by REL, where x is put equals to L. So it is the average drag coefficient. This is the local skin friction coefficient. This is the average coefficient of drag. This is your wall shear stress. All these values comes for the laminar flow. Then comes these two questions, which says the result for laminar boundary layer for flow path of a path on a flat plate are based on the velocity distribution, which has linear no, parabolic yes, logarithmic no, 1/7 no, that comes in the turbulent. So the correct answer is parabolic variation. So one must know that Blasius had many profiles for different cases, out of which the standard ones were the parabolic profile given by the ratio u by u infinity equals to 2 eta minus eta square, then cubic profile 3 by 2 eta minus 1 by 2 eta cube, and the linear profile. But when asked for flow path on a flat plate, it is generally considered to be as the parabolic profile taken. Then the next question asks if the Reynolds number in a boundary layer is more than this number, that is 5 into 10 to the power. This is a golden number for boundary layer theory. If it is less than this number, then you will have the laminar flow, but if it is more than this number, you are bound to go with the turbulent flow. Often Reynolds number is also written in this form: velocity times x by nu, where nu is the kinematic viscosity. Then let's see the next question. It says the boundary layer separation occurs when the pressure gradient is 0, no. When the pressure gradient is negative, no. When the velocity increases, no. The correct answer is when the pressure gradient is adverse or positive. So you see the development of the pressure, the velocity profiles as the pressure changes. In this region the pressure is negative, but the flow is in acceleration, that is the velocity is increasing. There comes a point when there is a sudden change in the pressure gradient from decreasing to suddenly it becomes an increasing pressure gradient. But what it does to the velocity is it decreases the velocity, and hence the velocity profile starts changing after this point. Here comes a point where the velocity is at the verge of separation. Hence you could see that in this region the velocity has already turned 0, and here comes a point where the velocity has started separating. You see the deceleration is so much, the decrease in velocity is so much that it starts flowing in the reverse direction. So that is a separated flow. Hence the boundary layer separation occurs when the pressure gradient is adverse or positive. Then comes this question that the distance from the pipe boundary, let us say the distance is y, at which the turbulent shear stress is 1/3 the wall shear stress. The formula is simple. Even in the turbulent shear stress, it is given by tau equals tau naught 1 minus 5 by r. We simply put tau as tau naught by 3, and after calculating we get y equals 2 by 3 r. This formula is the important formula. Then comes this, the boundary of channel, where Ks is the average height of the surface roughness and delta dash is the thickness of the laminar sublayer, is said to be rough. Now one has to remember that irrespective of the flow being hydrodynamically smooth or hydrodynamically rough, there will always be a laminar sublayer in the turbulent flow. So one has to remember that laminar sublayer is always formed in a turbulent region or turbulent flow. and it is always close to the no slip condition or the rough surface. In the hydrodynamically smooth, these protrusions or roughness protrusions are always very small, and the ratio of this k, where k is the average height of these protrusions, to the delta dash, where your delta dash is the distance of the laminar sub layer from the no slip condition surface. It is if it is less than 0.25, it is considered to be smooth, but in this question they had asked us rough. It will be when it is greater than 6, and when it is in between 0.25 to 6, it is considered to be in a transition zone. As I said, it is in the transition zone, and if it is greater than 6, it will be rough. Then it says the velocity distribution in turbulent boundary layer is in the turbulent boundary layer, the velocity distribution is nothing but logarithmic. It is shown by this formula, where the local velocity is written as u max plus 2.5 u star, where u star is nothing but shear or friction velocity, log of y by r. Shear velocity is given by under root tau naught by rho. For this question, we have the thickness of turbulent boundary layer at a distance of x from leading edge over a flat plate varies as we know. The thickness of boundary layer in a turbulent flow is written as 0.376 x by re x to the power 1 by 5. So delta x is directly proportional to x to the power x1 by 5. This comes out to be x4 by 5. That is x to the power 0.8. Hence the first option. The next question asks us to find out the wrong one in respect to the boundary layer thickness. How does the boundary layer thickness increases or decreases with the direction of flow, with the approach velocity, kinematic viscosity, and pressure gradient? We know that in our boundary layer development over a flat plate, the layer subsequently goes like this, and we know that the boundary layer delta x keeps on increasing as we move from laminar to turbulent flow. The delta just simply increases. So in the direction of flow, of course, it increases. Then next it says it decreases as the approach velocity increases. Now approach velocity increases means when the approach velocity, that is the velocity coming in the opposite direction, is coming towards the flow. In that case also, as approach velocity is increasing, it decreases the boundary layer thickness. Then comes increase in kinematic viscosity. We know that delta is written in terms of Reynolds number. Now this Reynolds number itself is written as rho Vx upon mu, or we write it as u dot x upon nu. So if you increase the kinematic viscosity, you are bound to decrease the Reynolds number, and since Reynolds number is inversely proportional to the square root of this thing, if you decrease it, it will eventually increase. Hence this statement is also correct. So is this. The only remaining statement is this. Hence this one is the wrong. Why is it wrong? It says that it is not dependent upon the pressure gradient, which is wrong. We know the pressure variation in the boundary layer thickness or the boundary layer. We know that as it approaches a point where before the stagnation point, the pressure gradient is less than 0, but when it is greater than 0, we know that it starts hindering the development of the boundary layer and it starts separating the flow. Hence pressure does affect it, and we can see that at the point when the pressure gradient is 0, the saturation risk is 0, but when it is adverse or when it is positive, it causes delta to swell, that is, it leads to separation of it, whereas when it is decreasing, it causes the delta to remain thin, or it retards its growth. Then comes this question which asks that a smooth two-dimensional flat plate is exposed to the wind velocities. The velocity is 70 kilometers per hour, and if laminar boundary layer exists up to the value of Rex is given to us as 3 to the power 10 to the power 5, and kinematic viscosity is given as 1.49 times 10 to the power minus 5 meters square per second. It has asked us what would be the maximum distance up to which the laminar boundary persists. Now, since they have mentioned that it is a laminar flow, we know delta is given as 5x by root under Rex. And what they have asked us is that they have given us the Re value, and they have asked us for, sorry, my approach was wrong. The approach was like this. You had the Reynolds number. We know Reynolds number is written as rho u x upon mu. In this question, or we can, in terms of kinematic viscosity, we can write it as mu x upon mu by rho, which is mu x upon nu. So in this question, Rex is given to us, velocity is given to us, the kinematic viscosity is given to us. We have to find the x. So let us find out. Since these units are in meter per second and answer is also meter, we will convert this 70 by 3.6 meter per second. We can roughly take it as 35 or 3.5. That will be 20 meters per second. So let us calculate Rex. Rex will be 3 into 10 to the power 5. We can take velocity as 20, x we have to find out 1.49. we can take it as 1.5 times 10 to the power 5. This becomes 40. We get, this will cancel it out. X as nothing but 9 by 40, which gives us around 0.225. So C option is the closest one. Then comes another question which asks us if delta 1 and delta 2 are laminar boundary layers at the thickness at a point m distance x from leading edge, when the Reynolds number of the flow are this and this, then the ratio will be. So we will be using this formula where we know that in laminar boundary layer delta is taken to be as directly proportional to x, because this is nothing but x by root x, that amounts to root x only. So simply by taking the ratio at different x, we can find that delta 1 by delta 2 is nothing but root under x1 by x2. What we have is, or since in this question we have directly been given Reynolds number, we can simply use this variation, that is delta 1 by delta 2 is root under Re1 by Re2, and since Re1 is given as 100 and Re2 is given as 484, that will be taken as, I believe it is 22's square, 484, yeah, 22's square by 10 square root under, that will be nothing but 2.2, hence the answer will be 2.2. This question also comes sometimes when we have to use this ratio where delta 1 by delta 2 is root under x1 by x2. Then comes this question which asks that which of the following condition holds true at the point of the boundary layer separation. So we know that at the point of the boundary layer separation, the ratio del u by del y, that is change in the velocity gradient, stops equals to 0, because the velocity approaches 0.99 u stream velocity, hence at the boundary layer separation, at the point where the boundary layer separation occurs, hence we know that tau is mu du by dy. So when this term is 0, your shear stress will be 0, hence at the point of the boundary layer separation the shear stress is 0. The next question asks the thickness of the laminar boundary layer on the flat bay at point A is, that is delta x has been given to us as 2 cm, or delta 1 has been given to us as 2 cm and delta 2 is given to us as 3 cm, and they are saying us what is the distance of A. So let us say if A was point here, it was x1, and we have another point x2 and it is 1 meter, that is x2 is x1 plus 1, or we may write x and x plus 1 as A and B. We know just above we discussed that delta 1 by delta 2 is written as x1 by x2, which is the distance from the leading edge. x1 is nothing but x and x2 is x plus 1. Delta 1 by delta is nothing but 2 and 3. Its square will give you x plus 1. Moving on, we'll get 4 by 9 equals x by x plus 1. On solving, we can say 1 plus 1 by x is 9 by 4. So that means 1 by x is 5 by 4. So x becomes 4 by 5, that is nothing but 0.8. Hence B should be the answer. Then comes another question which asks the boundary layer thickness at a distance of 1 meter from the leading edge kept at 0 angle of incident is 0.1 centimeter. So the delta 1 is nothing but 0.1 centimeter at the rate x equals 1 meter. The velocity outside the boundary layer is 25, that is u infinity is given as 25 meters per second. The boundary layer thickness at distance of 4 meter is since within one has to, for this question one will have to both check this one thing, which is we'll simply do delta 1 by delta 2 is root under x1 by x2. We have delta 1 at the rate x equals 1, x1 equals 1 meter, and they are asking us delta 2 at a distance of 4 meter. So 0.1 centimeter by delta 2 is root under 1 by 4. This was just to confuse us. So 0.1 by delta 2 is 1 by 2, delta 2 becomes nothing but 0.2 centimeters. Then comes the velocity distribution question, where this is given. We have asked displacement thickness. We know that displacement thickness is represented by delta star as integration 0 to delta 1 minus u by u infinity dy. Well, we'll simply calculate it. 0 delta 1 minus y by delta to the power 1 by 7 dy, and then while calculating it we can find out this y to the power 0 to delta minus 1 by delta y integration y dy to the power 1 by 7 dy. That will be y minus 1 by delta y to the power 8 by 7 by 8 by 7, that will make it y minus 1 by delta 0 to delta times 7 delta to the power 8 by 7 by 8, that will y minus 7 by 8 del to the power 1 by 7. One second, I might have done something wrong here, which is, oh yes, it was not delta but 1 by 7. 8 by 7 minus 1 by 7 will be delta simply, and this will also be delta minus delta, that will be 1 by 8 delta, that is delta by 8, hence the answer will be delta by 8. Then wake is a region of high pressure. No, it always occurs after the separation point. This is an important point. Wake is a region of recirculating turbulent flow immediately behind a moving or stationary body. It is accompanied by flow separation and the turbulence. The distance measured perpendicular to the boundary of a solid body, by which the boundary should be displaced to compensate for the reduction of flow rate on account of boundary layer formation, is nothing but boundary layer thickness. And if for the same statement they had asked that distance by which the boundary should be displaced to compensate for the reduction in momentum, then it would have been momentum thickness given by theta. If they had said to compensate for the reduction in the kinetic energy, then it would have been energy thickness delta star. Again, when you will solve it, comes out to be delta by 2. Yeah, so now for this time these only questions would be it. That would be our revision video.